The modern understanding of atomic orbital theory tells us that electrons reside in shells. Okay, Bohr established that. There's also a number of subshells, s, p, d, and f orbitals. And what we're going to do now is take a look at this electron configuration, but we're also going to include orbital notation. These are these blocks up here that show us the directions that electrons are spinning in, how they tend to spin in opposite directions within an orbital, and how within an orbital group they tend to spread out. This is Screencast 5.9. We'll be learning to describe the entire electron configuration of atoms with this orbital notation. Let's go ahead and begin. Why does it matter? Ooh, that's a good question. Okay, the electron configuration with orbital notation. It tells us where the electrons are in an atom in great detail. Let's pick up with lithium. It has 3 electrons in its uncharged state. So let's go ahead and show what it must look like. The electron configuration is 1s2, 2s1. That simply means in the first shell there's 2 electrons spherically arranged. In the second shell there's also a larger spherical orbital that holds 1 electron. We can show, using electron configuration, a little more detail. That's 2 electrons. We now know that they have opposite spins. This is indicated by the up and the down arrow. It simply means that they have opposite spins. And the orbital in the second shell is unfilled. It has 1 electron in it. Fine. That's the electron configuration. That's the orbital notation. This opposite spin concept is known as the Pauli Principle. Electrons pair up in atomic orbitals with opposite spins. Let's go to carbon, 6 electrons. We begin with the 1s2 orbital, as we always do. The 2s2 orbital. Notice the Aufbau order in practice here, this strange arrangement. And then 2p2 should do it. We only need 2 more within the p orbital group of the second shell. So there's our first pair of electrons. Pauli Principle is applied. Here's the second shell. Pauli Principle is fine. Now, in the second shell, you might be tempted to go like this, but that would be wrong. There is a rule, which makes sense, that says electrons like to spread out. So let's put a big X there and redo it. That's how they do it. Given the opportunity to, they'll spread out. They couldn't here, it's filled up. They couldn't here, it's filled up. But for the 2p group, it has 6 electrons and they will tend to spread out. This teaches us a lot about bonding, and later we'll learn about something called lone pairs. So it is consistent with observed phenomenon. So this is the observation that electrons spread out within orbital group. It's called Hund's rule. There it is written out right there. Spread them out. Okay, let's do a big one. Sulfur with 16 electrons. Let's work our way through the Aufbau order. You know, it gets easier with time because it's always the same deal. 1s2, 2s2, 2p6, that's 10. 3s2 is 12, and 3p4 is 16. Did we spread them out as much as possible? Full, 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 full. Not full, but spread out. I gotta pair up somebody. So this looks good. And this is the electron configuration of sulfur. This is the orbital notation for sulfur. And this is Screencast 5.9.